Hi all, this is Alan with Bothell STEM Coach, and today we are continuing on with the AP Physics 1 free response questions. We're looking at electrostatics. Now I need to read through the problem and make sure, before you attempt the problem, I want to make sure that there are no parts of the problem that you're unable to do because, again, these are from the AP Physics B. I think you can do this whole problem because it's all qualitative. Yeah, magnitude of electric force. Yeah, okay. So, again, attempt the problem on your own, and then come back after you've tried it. So I have three particles on a coordinate axis shown. Particle A is a charge of negative 0.2 nanocoulombs. It is initially on the y-axis here. Then, okay, so, I mean, they're just saying where everything is. Calculate the magnitude of the net electric force on particle A when it has a y equals 0.3, when it's here. Okay, so here, I want to calculate the force, or I want to do the force. Now, it's feeling a force from QB, and it's feeling a force from QA. Now, QA has a negative, this is negative 0.2 nanocoulombs. I'm going to write these down. QB is 0.3, positive 0.3 nanocoulombs, and they're also 0.3 nanocoulombs. Okay. So, the force from QB on this one, because they're opposite charges, right? They're attracted. So QA is attracted to QB, and QA is attracted to this QB also. Okay. Now, I think by symmetry, because they're the same distance away, these x components are ultimately going to be the same, and the angles. So the net force is really going to be downward. Okay. But I'm going to do it as an exercise to compute what the actual angle is, because in a more difficult problem, perhaps you don't know where the angle is, and you may want to know what the force in the x and the y direction might be, I think. Let me think. Yeah. The way you would compute the angle is just from this triangle. Like, you just know the distances here. But, okay, so let's first compute the magnitude of the electric field. Or actually, this is just calculating the electric force. So this is just using Coulomb's law. Coulomb's law is K Q1 Q2 over R squared. That's sort of the magnitude. And, yeah, I usually write it as this. The magnitude. I use the direction based on, like, just the picture. So the magnitude of the force is K. Q1 is, in this case, Q1 is QA and QB. So it's 0.2 nanocoulombs times 0.3 nanocoulombs all over their distances. So we got to do the distances. This is 0.04. This is 0.03. That's a 3, 4, 5 right triangle, by the way. So this distance is 0.05. I do this distance here. So it's 0.05 meters squared. Okay, so that is the magnitude due to this guy, right? And so don't forget that, let me write it out, because you want to put everything in SI units. So K is 1. Oh, crap, I actually don't remember what Boltzmann constant is. They'll give you a formula sheet, but I don't remember it off the top of my hand. I definitely don't memorize equations like that, or memorize constants like that. It's 9 times 10 to the 9th Newton meter squared per coulomb squared times 0.2 times 10 to the nano is 10 to the negative 9 coulombs, and then 0.3 times 10 to the negative 9 coulombs, and then divided by 0.05 meters squared. Okay, so we just plug that into the calculator. 9E9 times 0.2E negative 9 times 0.3E negative 9 divided by 0.05 squared. So I found this is 216 times 10 to the minus 9 newtons, or you say it's 216, I guess, nanonewtons. It's a very small force. Okay. Oh, that's not, and that's simply the force due to this one here, right? But what I want to do is I want to consider the x and the y components because I need to add them up directly, right? And to do that, I need to know the angle, this angle that this is happening at. But because I know this is a triangle, this is a 0.04, 0.03, 0.05 triangle, the angle that it's at is tangent, or I know I can use any trig that you want. You can use sine, cosine, tangent. I prefer tangent. I would know tangent of this angle is opposite over adjacent, which is 0.04 over 0.03, which is 4/3. So theta would be tan inverse of 4/3. Okay. And then you can do that in the calculator. Actually, I have a little more elegant way to do it without a calculator. The x component of this force would be this magnitude times cosine of theta. So the x component of the force is 216 cosine theta, and the y component of the force is 216 sine theta. But cosine of theta, because this is the triangle, is adjacent over hypotenuse. That's 0.03 over 0.05. So that's really equal to 216.03, or 3/4 times 3/4. So 216 times 3 divided by 4 is 162. So in the x component, I have 162 nanonewtons. That's the force in the x direction. And the force in the y direction is 216 times the sine of theta, which is 0.04 or over the hypotenuse. So 216 times 4 divided by 5 is 172.8 nanonewtons. Now, QB is going to do the exact same thing. It's going to have the exact same force because this is still a 3, 4, 5 triangle just sort of flipped over. So it's going to have the same, this vector is going to have the same x component, right? When I mean x component, I mean this x component, this y component, and this y component, and this x component. The x components are going to cancel when I add these two vectors together, right? And so the net force is actually just downward twice as much. So the total net force of the electric force is 2 times Fy, and that's 345.6 nanonewtons. Okay? So some vector addition, vector math, maybe I haven't done in a while. Particle A is then released from rest, qualitatively described its motion over a long time. Well, it's going to go downward, and it's going to continue having a y component of vector. The force is going to be, in the y direction, it's going to be 0, right, as it gets to here, as it gets to this point. So it's going to fall downwards. Okay, so at this point, the force is downward, but you see, along this path, because it's going to move downwards because the force is downwards, so that means when I let it go, it's going to fall downwards, and the force is going to go to 0. And then as it goes in the negative direction, because it will pick up some energy, right? At this point, like, it will have, the force will cause it to move faster and faster and faster. At this point, the net force is 0 on it, because it will only have a force this way and a force this way, which will cancel each other out. But it will still have some velocity, so it's going to swing past. And then when it's on this side, it's going to have force in this direction and force in this direction. And so the net force is going to be upward in here. Okay? So then what it's going to do is, because it has the initial velocity, the force is going to slow it down. It's going to hit a point, and it's going to come back and forth. This is simple harmonic motion. I don't know if it's simple harmonic motion, but it's going to oscillate. It's going to go from this point to that point between y equals 0.05 meters, 0.03 meters to y equals negative 0.03 meters. So it's going to bounce between there and there. Okay. Yeah, I don't actually know it's harmonic, so I might not say harmonic, because harmonic implies it's a sinusoid, like it has a form of a cosine, and I don't necessarily know that it would have a force of a cosine. Yeah, it's definitely gonna oscillate. So I wouldn't specifically say simple harmonic motion. That's because simple harmonic motion has a very specific meaning. And in physics 1, you don't have to be too subtle in it, but it has a restoring force and it's periodic, which is true, but I don't know if it's exactly a cosine or a sine periodic function. So all I know is it's just going to be oscillate between the two. So anyway, hope you found that helpful. I'll see you in the next video. Thanks for watching the video, guys. Please leave a comment, like, or subscribe below to catch up more of the content. And see any links below. I offer free homework help on Twitch and Discord. See you guys in the next video.